Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Sean Welch, your host. I'm the host and producer at Data Science Central. I'd like to start our event off today by thanking Gurobi for sponsoring today's event. Gurobi is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. Today's webinar is entitled Prescriptive Analytics, the Data Scientist's Master Key to a Turbulent Future, to be presented by Gurobi. And before we begin, I'd like to briefly review the format of today's webinar. Today's event will be 1 hour long. We have one presenter who will introduce in just a minute. There will be a 10 to 15 minute Q&A following the presentation. And this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We will be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speaker, Dan Jeffrey with Gurobi. Dan is Senior Technical Account Manager of the Americas and has 20 years of professional experience in math programming and data science, working as a technical product expert and as a consultant. He has architecture and programming expertise with all major programming languages, math programming experience with Python, AMPL, and OPL, plus programming expertise with the AMPL Solver library. Today, Dan is a MIP fanatic working as a member of the Gurobi support team. Thanks for being with us today, Dan. We are looking forward to your presentation.
Thank you, Sean.
Sure.
Go ahead.
In today's Data Science Central webinar, find out why companies like Uber, Air France, SAP, and the NFL use prescriptive analytics for continuous innovation. Leading data scientists constantly expand their skill sets to provide more value to their organizations. The best strategy for taking on new tools is to focus on the return on investment of different project types. Mathematical optimization delivers extreme ROI for organizations that use it. Data scientists who make the leap into mathematical optimization suddenly discover dramatic cost savings and new efficiencies to offer their management. Dan, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Thank you, Sean. Well, so here we are. We've got a lot of people from the data science community attending today, and let's talk about what we hope to show you during this presentation. We'll first cover what is prescriptive analytics. We'll then cover why I think you should learn it, why we think you should learn it. Excuse me. Then we'll see a model so you can actually see what the practice of mathematical programming is like. And we'll talk about what are the hurdles to learning it and how you can go about learning it. So we'll cover all that today. But we should also talk about first how we got here. I understand you've all seen a white paper that covers Gurobi's use in Uber, NFL, and SAP applications. We'll talk more about what this technology is and does today, but why? I mean, the motivation here is actually that I believe, and Gurobi believes, data scientists are perfectly capable of taking on this new technology. It's always been a bit of a niche technology in the world of analytics, but we see more and more a combination of data science methods and mathematical programming to produce really cutting-edge applications. So I believe it's a really good tool to have in your toolbox and well worth the effort to learn it.
Dan,
so we first would like to...
Dan,
please go ahead.
This is Sean. On your screen, are you seeing some overlapping of the slides?
I am, yes.
Okay. Continue with your presentation, and I'm going to escalate this issue. Thank you.
Okay, well, first we could do the poll. We're going to do a poll now to see among the audience, which of you have different levels of knowledge for prescriptive analytics. So there will be some prompts on the screen for you here, and I'd appreciate your feedback because it'll help me tune the presentation to better fit the audience.
And the poll is launched. We'll keep the poll open for about another 30 seconds or so. The poll results.
So yes, let's see. Yes, I do. Okay, interesting. So this is pretty close to what I expected. The majority, which was a third of you, said you have heard of prescriptive analytics and mathematical programming. A quarter of you had not. It's a new subject. And 20% have used it, actually used prescriptive analytics. The remaining 12, almost all of the remaining people have learned about it in school, but a very small percentage are expert users. That's more or less what I expected. So I'm advancing, there we go, advancing the slide. So let's talk about what it is. And now, if you're like me, you want to see some code. That's why I come to these webinars. And I will not let you down. I'll show you some code and we'll go into it in some detail. But first, let's talk about sort of the basics, what it is. And now descriptive analytics and predictive analytics are the area where you're currently participating. I think these terms are more commonly used by people in the optimization arena because we want to show you where we fit. I don't know if these terms are commonly used among data science practitioners, but anyway, the categorization of analytics is broken down in this way. So machine learning, for example, is frequently used to do machine reading or machine vision applications where you're trying to classify something to know what it is. Predictive analytics, machine learning again is used to predict, for example, the outcome of a marketing campaign, what we would expect certain individuals, how they would react to a particular advertisement, and that sort of thing. And then lastly, prescriptive is the area where I live in mathematical optimization. There's a lot of different terms for this, and we'll go into that next. But I think it helps to know the difference. So the purpose of prescriptive analytics is to prescribe, to find the best answer to a complex set of choices. So it's a perfect analogy to think of a doctor writing a prescription to a patient. And but it'll be very precise in the sense of a drug prescription. Obviously, the prescription has to be very precise, and you don't want it to be too much or too little. But with a mathematical optimization or prescriptive analytics, we're trying to give you the best possible answer to this complex set of choices. So unlike a drug prescription where dosages come in standard quantities like 20 milligrams or 50 milligrams, here we're trying to figure out the exact mathematically provable best answer to that problem. In the case of the drug prescription, it might come out to be 32.75 milligrams per day. We don't know. But that's the purpose of mathematical optimization. I think I accidentally clicked there. Let's also get used to some terms, because the word optimization is very fraught with mixed meanings. So in your world, it means usually it's used to refer to optimizing a machine learning model to produce the right results. But we mean some very different things here. So optimization is a term we use internally in our world, in the world of math programmers. But the more general term is mathematical programming or math programming. And a more precise term than that is mathematical optimization. We've begun to use that lately as we get more and more data science practitioners interested in our world. So the shorthand version of that is MO. But you'll hear, sooner or later, you'll hear people like me just using the term optimization. Please do remember it's a different word than you're used to thinking of. It means mathematical optimization. That's what we're trying to say. Now, this science has existed since the 1940s. It's a very old term. In fact, the term programming, meaning computer programming, came from this world. It was first applied in the sense of writing a mathematical program. So it's a really old science. But and it covers all kinds of different problems. There are different algorithms used to solve these different problems. And Gurobi does that for you, by the way. You don't usually have to worry too much about whether you're writing an integer program or a continuous linear program when you're getting started. You just write the program and tell Gurobi to solve it, and it will. But there's a whole family of these problem types. My encouragement to you right now is don't worry about that yet. It'll become an important thing down the road, but as you're getting your feet wet here, there's a lot you can do in a little time without worrying about the different algorithms involved in the beginning. Now, this science, or this type of math, applied mathematics, reached broad viability in the late 1990s, mainly in the utilities, petroleum, and data, or rather supply chain world. So those three categories were kind of the pioneers of broad applications, kind of going into deployed architectures in the late 1990s. And it was a factor of performance. So I'm showing a performance chart on the right. It's the progress of the Gurobi solver since we started. We started this company in the mid-2000s, but the people involved were involved with other solvers prior to that. But since the year 2000, we have algorithmically improved Gurobi, actually since the year 2008, about 70-fold. That's pure algorithmic improvement relative to our start. That's pretty stunning if you compare it to other technologies and if you factor out hardware. But if you factor hardware in, then we can say that we're millions of times faster than the best solver was in the year 2000. So think about what that means. It means that you can solve problems today that were impossible even 5 years ago. And there's lots of literature still commonly touted that shows certain kinds of problems are impossible to solve, when in fact they're absolutely not. So do beware of the literature on this. You'll hear it in, well, I won't go into detail, but just remember that the world is changing quickly, and if you hear that the problem you're trying to solve is impossible, maybe you should check other sources first. Okay, so let's start with a classic example. This is an optimization problem called the traveling salesman problem. We have names for all the categories of problem types. Here again, I'll caution you not to worry too much about that. You can learn these as you go along. But just know that when we throw out these terms, like the traveling salesman problem, we even abbreviate it to TSP, that they were just referring to a particular kind of a problem. It's modeled in a particular way. Now, in this problem, we're trying to find the shortest route between a bunch of cities, imagining a traveling salesman starting out from his home city, trying to visit all these other cities. We have 95 cities here. We want to visit each one once and only once. We don't get to go back. And we must end up where we started. So that means we have 94 factorial possible routes. That's a big number. It's 1 to the 146th power, or 10 to the 146th power. So it's this number here, whatever that is, a huge number. So there is only one best answer to this. If we factor out that we don't care where the starting city is because it's a loop, so we really don't care about that. That's why it's 94 factorial instead of 95. So there is only one best answer, unless there are two cities with identically the same distance apart. Unlikely. So this is you could approach this as just a brute force attack with it. You could take 4 cities, for example, to get your algorithm going, and you could say, well, I'll try all the combinations of routes that address these 4 cities, and then I'll just pick the shortest one. Yeah, you could do that. You could, better yet, you could do it in code, and it'll be done in seconds. That's 4 cities. What about 10? That's going to take a while. 95, I don't know how long it'll take. I actually started on this to see. I didn't get it done in time, but it would take a very long time. And in practice, unpractical amount of time to solve that problem. So people started trying to come up with new ways to do this. So I don't want you to spend too much time thinking about how you would solve this. I'll begin to show you that as we go along here on another problem type. But we do have an example that comes with Gurobi that does exactly this, and here's the solution. It took Gurobi 1.49 seconds to solve when I ran this. I ran it on our demos site. You can go to demos.gurobi.com and play with this at any time you like. It's a live thing. If you have a login to the Gurobi website, you can go there and play. I think it's great fun, and there are different problem types there that you can play with and see what optimization's about. This used to be regarded as totally unsolvable. And even today, as I said, some literature will tell you this is an unsolvable problem, and they'll cite other technologies as giving the great new hope for solving this. Well, these have been solvable since the 2000s, depending on the problem size, but totally solvable. And it really gets more complex when you begin to add things to this. So the really big and difficult problem of this class is a vehicle routing problem, where you have time windows. You can only visit a particular destination during certain hours of the day, and maybe you will allow a certain number of routes. Maybe you have 6 trucks, so you say, okay, you can break this up into 6 routes if you want, and then let the solver find the answer. That's when this becomes much more complex, and that's true of all of the problems that we'll talk about and the ones that you'll learn about later. The devil is in the details, and a simple example like this, not too bad, but when you begin to add what we call side constraints or extra rules to the problem, things get very complex and hard to solve very quickly. Okay, so there's a brief taste of what it is. Let's talk about where it's used. The short answer is everywhere, in every large organization. So processes and decisions that involve, first of all, involve well-defined and concrete choices. You can't have gray areas as you are used to having with a machine learning model. That's great for gray areas. It decides what the meaning of the data is. This is a totally different technology in that way. We're taking the data verbatim and we're trying to decide what to do with it. We're trying to write a prescription. So there's no gray areas involved here. The choices you make have to be definable in mathematics. And usually it has to be a large scale or expensive project because the labor involved in writing the model is significant. And a good commercial solver like Gurobi is not an inexpensive product. So usually we see this for medium to large size organizations, but there are plenty of exceptions to that. But just usually think in terms of a larger budget is going to have to be involved. And always we're looking at some limited resource. And that can be most often money or time in a scheduling application, or it just really could be any physical resource as well. So, but just look for something that's constraining your choices. In the traveling salesman problem, we had what was a constraint? I guess we just wanted to make sure we had the shortest route, so we were trying to save time. So I guess time was our constrained resource in that case. And also, this works only when usually, that's not quite true. My bullet here should change to say usually is used only when the best answer will do. We're also good in a lot of application types at finding a viable answer very quickly. It's part of the focus of what we do. So with machine learning, you can frequently find a viable answer to different kinds of complex choices, not just machine learning, other kinds of technologies, genetic programming, things like that. But when you need to know the best answer and know that you've got the best answer, that's when optimization or prescriptive analytics are your friend. And that's really the message I want to get across to you here. This is a technology you don't have today. And it's something extremely powerful. And I want to show you why it's powerful and why the reason I'm doing this webinar is that I feel that you should learn this. It's really going to be the most valuable technology you can pick up today, in addition to what you already know. Okay, so, and I mentioned budget here. So those are the kind of the criteria. This is a slide by itself because it can frequently be difficult to identify whether you've got an optimization problem or not. Usually because when you're interviewing the business stakeholders, they don't think in these terms and they're not giving you the information you need to really pin it down. So we'll talk a bit more about that kind of thing as we go ahead.